the assignment for chapter 1, so assignment number 1, due Friday, which is the 1st, right? The 29th, by 5 p.m. Okay, and I gave specific instructions last time about how to do that. I guess I'll go over them again. So complete your assignment with pencil and paper, and then every problem starting on its own page, please. Don't finish a problem and then start another problem on the same page. Make them on separate pages for clarity and ease of grading, please. Put your papers in numerical order. Scan using your smartphone with Adobe Scan or Cam Scanner. So these are free apps that you can get, and they both are pretty simple and work very well. Or I'm sure there's other similar ones out there. And then if you do use a flatbed scanner, set the resolution down and set the size to 8.5 by 11. So I'll post solutions at 5 p.m. Okay, so due by 5 p.m. and then I post solutions right after that. All right. Does anybody have any questions on the assignment? So let me pull it up here.
I had a question on, well, it's not really a question. It's kind of like I'm stuck on 3A and 3B.
Sure. Why is this not working? There we go. Okay. Come on now. All right, 3A, 3B. So last time I gave you a clue as to how to start 3B. Did we try that one yet?
Yeah, so you said use associative and distribution. And I did that.
And then don't forget the idempotent rule. So after you use distribution, idempotent should apply right afterwards.
Yep. That was the next step that I did.
Okay. And then you should be able to use distribution again.
Okay.
Right, because what are you left with? You're left with, at that point, you're left with A and B, or I guess, no.
I think it would be
identity, actually. You want to use identity, I think. A or A and.
after idempotent, use identity.
Yeah, idempotent. Oh, hold on. Wait, I think I've got this wrong. A or A and A or B. So with idempotent, this gives you A and and A or B. Yeah, you want to use, yeah, you're going to want to use distribution after that, because you're going to be, after idempotent, you're left with this or A and B not. Right?
Yeah. So
So,
then you would have A and A, or A and B, or A and B.
let me see. Hold on a moment. Get a piece of paper so I can do this. Um, so A or B or A and B. So so this is A or B or yeah, it's working out. So once you're to this point here, then you want to use distribution and factor out the A. Right? You did that, you're saying?
Yeah.
Yeah, so that gives you A and, parentheses, A or B not. And then you can use complementation, well, associative and then complementation, because A or B not, the B or B not is 1, right?
Would it be so after the distribution step I got A and A, or A and B, or A and B not?
So after distribution, it should look like this. A, so it's A and, right? So when you're factoring A, it's A and then these two terms, A or B, or this term, like that. So after you
Oh,
factor the
okay.
A out, that's what it looks like. You got that? Or was it off a little bit?
Mine was off a little bit.
Okay, all right. And then from there, use associative. Associative,
Okay.
complement, annihilation, identity. It should work out pretty quickly from that point.
Okay, thank you.
Sure. Anybody else? Any questions?
Are you able to re-explain? I know last class we talked about not high isn't low, it's reasonable. Can you re-explain that?
Oh, the negation of something. When you negate something, or I guess this is the wrong day. No negation. Given a proposition P, the negation, right, is literally in English, or in whatever language you're using, not P, right? But not P doesn't necessarily mean the antonym of P. Not P is linguistically not the same as the antonym of P. Only when when there's only two properties. When P is either sort of on and off, is one of two properties. Is not P and the antonym of P the same thing. So, like, for example, P equals the switch is off. The switch is on, we'll say. The switch is on, right? So then not P is the switch is off, because not on is off. There's only two possibilities for a switch. It's not on, or it's off. So not off is on, not on is off. However, when you have a range of possibilities, right, to say it's not one possibility means it's anything from that range, other than the one that it is. So, for example, let's see. So P is Peter got a 36 on, well, there's no antonym here. There's no antonym. So Peter, so the food is expensive. I mean, of course, this is a value judgment. But assuming it has, assuming that it has a good, assuming it has a well-defined meaning, it's a value judgment. The food is expensive. I mean, what I would consider expensive, and what what's his face, the Amazon guy. What's his name? Or like what I would consider expensive and what Bill Gates might consider expensive are two different things, perhaps. But I mean, assuming it does have a definite value. So P is the food is expensive. In this case, not P is, or P naught. Sorry, P naught is the food is not expensive. It doesn't mean it's cheap. Right? It doesn't mean it's cheap. The antonym of expensive is cheap. Right? And in this case, what does not expensive mean?
Reasonable.
Reasonably priced. right? Reasonably priced. Or affordable, right? The food is affordable. Affordably priced. Which could mean anything. It could mean the food is very inexpensive, or the food is got a moderate price. Like I don't know, everything's expensive nowadays as far as that goes. For me anyway. I got 4 kids, so anytime we go out, I mean, it's a huge cost. Like Chili's or something, right? Food is reasonably priced at Chili's. All right, you see what I'm getting at there with that. All right, I mean, not
Yeah, I think
expensive.
so.
There's a whole range of things. Not expensive could be affordable or cheap. But not expensive. Affordable sort of encapsulates it better. Or something more definite would be something like this. P is something like this. Peter got a perfect score on the test. All right, so P naught is, Peter did not get a perfect score on the test. Right, which could be the same as, but well, there's no antonym of perfect necessarily. Didn't get a perfect score. I mean, antonym of perfect score would mean like maybe rate a terrible score or something like that. A terrible score, but I mean a terrible score could be, but not perfect doesn't include just terrible. It includes anything less than the top score. All right, so you could say Peter got less than the top score possible, rather than like a terrible score. Okay. All right. But sometimes there's there's the antonym is right. The antonym of even is odd, right? Not even is also odd because there's only 2 possibilities for an integer. It's either even or odd. There's no other state of being as far as parity goes. All right. Anything else, guys?
When we're doing the negations on the homework, do we need to write it out in propositional logic first and then like do the negation that way and then write it in words? Or
You
can we
don't
just write
have
it
to,
in?
but like it's a good exercise for you to do that at this point.
Is that something we'll be tested on? Like writing
Oh
it?
yeah, I mean all of the test is going to be this stuff.
Right.
If I ask you to write the negation, all I'm asking for is the negation. I mean, you don't have to go to propositional logic first. I mean, later on you'll be able to do it without going to propositional logic. But I think it's a good exercise for you to do it that way now.
Okay.
Okay. Anyone else? Alrighty. So Wednesday you can ask questions again. All right. If you haven't gotten started on it, please do. So we'll start on chapter 2, and I will have a assignment for chapter 2 posted by next time. But we'll just start on chapter 2 at this point. So as far as the logic of human logic goes, propositional logic is not the end all be all of it. There's predicate logic, which is still not the end all be all of it. Things go a lot deeper than that. Although predicate logic is usually, for most purposes, it's pretty good. Okay, so definition. A predicate is a statement with a variable entry. It's a statement or proposition with a variable entry. Let me write it that way. Or proposition. The predicate is neither true nor false, until we somehow know something about the value of the variable. Okay, so for example, so e of x is going to be x is even. That's a predicate. And these have to be full sentences, complete sentences. Okay? So what's a sentence consist of at the very least in English? At the very bare minimum, what's a sentence consist of?
An object.
Subject first, right? Subject. Then three things.
A verb.
A verb. And then the object, right? Subject, verb, objective, or sometimes that second part is called a predicate, although I don't want to use that word here. Because this is a different meaning of the word predicate than the sentence structure thing. So subject, verb, object, direct object, or whatever it might be. So at the very least, that's what you have. Okay, so e of x is even. X is the subject, and even is the direct object, and is the verb. So for example, e of 5 is false, because 5 is not even. Right? E of 4 is false, or true, sorry, is true. E of square root of 2 is false. If it doesn't really make sense, I mean, you don't talk about numbers other than integers as being odd and even. You don't talk about fractions being odd and even, or irrational numbers being odd or even. So if somehow the subject's value, that value of x, doesn't make sense within the predicate, you just say false. Okay, so that's one example. Here's a two-variable predicate. X plus y equals 10. And so x plus y equals 10, so S37, that's true. S73 is true. S44 is false. Okay, just because you have two variables doesn't mean that they couldn't have the same value. So, two examples of predicate: a single variable predicate, double variable predicate. With double variable predicates, see, with this one, it's sort of symmetric in x and y because, addition is commutative. So x plus y is 10 if and only if y plus x is equal to 10. But I mean, such things don't have to be that way. If you said pxy, like x is the parent of y, right? So then if p, like p of Doug is the parent of Jake is true, then P of Jake, so like Jake is Doug's son, to say that Jake is the parent of Doug is false. All right, so things don't always have to be symmetric like that with a two-variable predicate. All right. So other than just substituting in values for the variables, for the variables in a predicate, we can also quantify variables over a specified domain of possible values. Domain D of possible values. So there's two types of quantification. So the first type of quantification is called universal quantification. And it goes like this. So use this upside down A. For all x, P of x is true. Sorry. For all x, P of x means for all x, P of x is true. Or every x makes P of x true. Or each x makes P of x true. Or something to watch out for is the following. So for all x, P of x means, these sorts of things in English. For all x, P of x is true. Every x makes P of x true. Each x makes P of x true, or something like that. But it could also be stated in the negative. So something like this, for all x, P not x, means no x satisfies P of x true. So it could mean every x makes P of x false, or it could say no x makes P of x true. Let me write that down way over here. Or all x All right, so universally quantifying something, it goes along with saying every x or all x or each x, but also when you say no x, that's also universal quantification. It's just quantifying something in a negative sense. right? No X, so no horses are purple. No horses are purple. When I say no horses are purple, that's universal quantification of horses. It means every horse is not purple. Right? No horses are purple means every horse is not purple. So that's something to keep in mind. So formally, we say that for all x, p of x is true over domain D when p of x is true for any x chosen from D. All right, so p of x is true when x is chosen for any x chosen from D. For every x in D or all x in D or something of that sort. So, for example, so D equals the domain set of all horses. So in this case, and p of x means x is purple. Right, in this case, for all x, p of x is false. Right? For all x, p of x is false. But if we were to change the domain, so D equals, the set of all. So what are some things that are always purple? The set of all, what? Got a good idea. Violets, great. The set of all violet flowers. All right, then P of x equals x is purple. All right, in this case, for all x, P of x is, actually say roses are red, violets are blue. Is violet blue or purple? I always kind of get confused about that. The set of all Murex snails, that's a... Well, they're not necessarily purple, but they have purple in them. Gosh, I never thought it would be so hard to identify purple things. We'll just say violet flowers. All right. Or if I was to say, some things that may be sometimes purple. So D equals the set of all what? Candies. All right, then for all x, P of x is false. I mean, even though some candies might be purple, especially the grape flavored ones, they're not all purple, right? So for all x, P of x is false. When you're talking where P of x means x is purple and D is a set of all horses or D is a set of violet flowers, makes it true. D is a set of all candies, makes it false. Numerical examples are sort of easier to deal with. Another example. So we'll say for all x, x is bigger than 0. All right, so let's look at this over a few different domains. So we'll say the domain is equal to the numbers 1, 2, 3, 4, 5, 6, 7, like that. Or D is the set of all positive and negative integers, -3, -2, -1, 0, 1, 2, 3, like that. Or D is equal to 0, 1, 2, 3, 4, 5, like that. Okay, so for all x, x is bigger than 0. Here, that's what? Over this domain.
True.
True. Here, for all x, x is bigger than 0.
False.
All. For all x, x is bigger than 0. Over this domain here. True, false? All means all. All means all.
So it's false.
It's false. In math, okay, in logic in general, whether mathematical logic or philosophical logic or symbolic logic, whatever kind of logic you're talking about, okay, things are brutally literal. It's always very literal. When you say all, you mean all. So here, for all x, x is bigger than 0.
False.
It's false. How many times does it fail? That x is bigger than 0. How many times is that false? Throughout this whole
One.
domain here. How many values in the domain don't satisfy x is bigger than 0?
1.
Just 1. And that's it. Okay? So, I mean, when you say all, it doesn't mean you missed you missed just one or something like that. You missed at most one or just a couple or something like that. No, all means all. So, there's no implied meanings here. All doesn't mean almost everyone. That's a whole different this is a whole different game in logic. It's called funny logic. Not funny logic, fuzzy logic. Almost all, or sometimes, or instead of always or all, you have sometimes, or almost all, or hardly ever, things like that. It's a pretty interesting topic. Very popular in computer science nowadays. All right, so that's universal quantification. The second type of quantification is called existential. So backwards EX, P of X, means there is X, so there is an X, making P of X true. Some X makes P of X true, or at least one makes P of X true, or things similar to that. Okay? Formally, there exists X, P of X is true over domain D when there is at least one X in the domain for which P of X is true. Okay, so, for example, let's go back to this one here. So there exists X such that X is bigger than 0. So there exists an x such that x is bigger than 0 in this domain. Means at least one of the x's in the domain satisfy this, that x is bigger than 0. True? False?
True.
True.
True. Absolutely true. Does it tell the full story? I mean, if I explore the predicate x is bigger than 0 over this domain, and I said there exists an x, at least one x in the domain such that x is bigger than 0. Does it tell the full story? Well, no, it doesn't, because every x is bigger than 0. Doesn't make it false. Okay, it's inaccurate, it's misleading, or something like that, but in a very literal sense, it's true. Okay, it's just completely being literal when you're talking in basic logic, either true or false. Here, there exists an x such that x is bigger than 0.
True.
That's true. There exists an x such that x is bigger than 0. Let me change this third one. So we'll say -1, -2, -3, -4. So all these negative numbers, and then we'll put a 5 there.
True.
It's true. When you say at least one, that means at least one. Okay, it doesn't mean you have to have one or more than one or whatever. It's just one. Or how about this domain? Let's see, can I fit it in? Can squish it maybe. So d equals -1, -2, -3, so on and so forth like that. Here it's
False.
false. Okay. So universal quantification, existential quantification. Things get interesting when you try to stacking. You stack quantifiers together. When you have a predicate with more than one variable, you need more than one quantifier. And you can mix them. You can have existentials and universals, or all universals, or all existentials. But you get to express sort of more interesting ideas in this way. All right, so let's look at this. Well, let's see. So for every x, there exists y, p x y. Means, in English, for every x in the domain, there is some y in the domain which depends on x. Some y in the domain dependent upon x, for which pxy is true. So something like this. Every student at Wright State has a name. Every student at Wright State has a name. Your name's Jack, your name's Martha, so on and so forth. Okay? Every student has some name that's particular to that student, and that name, the person responds to that name because that's what they're named. If you stack them the other way around, it means something else. There exists x such that for every y, pxy is true. Means, in English, So the sentence here starts with universal quantification. For every x, there is a y. For every x, there is a y. Here, there is an x for every y. There is an x in the domain. Such that for every y in the domain, pxy is true. So there is a name that every student at Wright State has. Is that true? There is a name that every student at Wright State has. Well, it is true, but the name isn't Peter. What is the name that every student at Wright State has? We are the Wright State. What? Y'all know it. I'm sure you do. Starts with R. We are the Wright State. Not Raiders. Raiders. Everyone at Wright State is a Raider. Right? If you go to Ohio State, everyone's a Buckeye, or something like that, right? So I mean, it's true, but in a very different sense than the other way around. Or you could say, well, that's not my name. I'm not a Raider. In which case that would be false. But it's expressing some more complicated ideas. When you start stacking for all x, there exists y, and there exists x for every y. So, for example, for every x, there exists a y such that x plus y equals 0. For every, there exists an x such that for every y, x plus y equals 0. So let's look at these two statements over a few different domains. So the domain will be the entire set of integers, minus 3, minus 2, minus 1, 0, 1, 2, 3, dot, dot, dot. All right. For every x in the domain D, maybe I'll just write the, save myself some space. For every x in the domain D, so for every integer, positive or negative, there exists a y in the domain dependent upon x, such that x plus y is equal to 0. Is that true? Suppose that.
Yeah, that's true.
Yeah. If I chose x equal to 7, then the y is going to be negative 7. If I chose x equal to negative 2, then the y is 2. In other words, y is the negation of x, whatever that, negation in the numerical sense, whatever that might be. Right? But it varies. For different x's, you get different y's. Actually, for every x, the y is different than any other x. And then for x equal to 0, the y is also 0. So that's true. What about this? There exists an x for every y such that x plus y is 0. There's one x. There's one x that's false. Totally false, right? There's nothing. I mean, if I said x is equal to 7, well, 7 plus y isn't always 0. It's only 0 in one instance, when y is negative 7. Right? Even if you said x equal to 0, if I said x is equal to 0, well, 0 plus y isn't 0. Unless y is 0 itself, but that's not everybody. Different with multiplication. For every x, there exists a y such that x times y equals 0. And then there exists an x such that for every y, x times y equals 0. Alright, for every x, there is a y such that x times y is equal to 0. Does that work here?
Yes.
Yeah. There's one particular x in the domain such that for every y in the domain, x times y is equal to 0. What's that special x?
0.
0. When you say x is equal to 0, when x is equal to 0, it doesn't matter what y is. X times y is 0. Right? So this is kind of like, that old saw, all for one and one for all. So everybody is for one. That's this one. And then there's one for all. It kind of means the same thing, but anyway, it sort of plays to that idea. What if I had this domain? 1, 2, 3, 4, 5, 6. Just the positive integers. Which ones are true, which ones are false?
The first one is false.
Yeah. Second one? They're all false. They're all false. You can never add two numbers in here and get 0, nor can you multiply two numbers in here and get 0. Never. Never. Right? What if I just added 0 in here? 0, 1, 2, 3, 4, 5, 6. Like that. Did anything flip from true to false? Or from false to true here? For every x, there exists a y such that x plus y is equal to 0. Only the last two are true, right? Because you got 0 in there. Right? So 0 times whatever is 0. So this one is true. For every x, there exists a y such that x times y is equal to 0. No matter what x is, pick y equal to 0. In which case, there exists an x equal to 0, such that for every y, x times y is equal to 0. These are still false. They're not always, this statement isn't always false. 0 plus 0 is equal to 0. Right? But not for every x do you get a y such that x plus y is equal to 0. Right? For x equal to 0, you take y equal to 0. For x equal to 1, well, you got nothing to help you out there. Okay, so the basics of quantification there's a lot more to talk about, but we'll do that next time. So I'll post the